Does anyone know what's special about today? Last day of notes. This is the last section in the book. What'd you say? Maybe after the AP test. Right? Yeah. Okay, so continuing on with yesterday's notes, we were looking at the areas inside polar regions. For this example, we're going to look at the area inside the cardioid. I think it's the same cardioid we looked at yesterday, but also outside of a circle. So we have two curves involved here. So we have our cardioid. Not quite that big. So we have our cardioid, and then we have a circle with a radius of 3. And we want to find the area inside the cardioid but outside of the circle. So the area that we're looking for is this red area here. Okay? And as we learned yesterday, when we use the integral of 1/2 r squared d theta to find areas inside polar regions, what we're actually finding the area of is sectors. And so really the most important step in these problems is to draw the radii that create the sectors. So I'm going to draw a whole bunch of radii here, all emanating from the pole. So I'm starting at the pole and drawing my radii to the curve until I have the whole red area shaded in. Okay? So when I did that, I did get all of the red area shaded in, but I also shaded in some area that I didn't want. Okay, so we're going to have to subtract that off. And so that would look like this. The red area is what we want. So the red area that we want is equal to the blue area minus the green area that we don't want, which is that area. So that's the extra area that we didn't mean to include. Okay, so we need to subtract that off. All right, so to get the blue area, we are going to write an integral of 1/2 r squared. So r is 2 times 1 plus cosine theta. We're going to square that expression. And to find the endpoints, or our limits of integration, we need to figure out what is this angle and this angle where the region starts and finishes. So notice that's where the two curves intersect. That's the intersection of the circle and the cardioid. And polar curves intersect when their radius and angle coincide. And so in order for these curves to cross each other, their radii had to be the same. And so if we call the cardioid R1 and the circle R2, then we want to know when is R1 equal to R2. When is 2 times 1 plus cosine theta equal to 3? If I divide both sides by 2, I get 1 plus cosine theta equals 3/2. Cosine theta equals 1/2. When does that happen? When does cosine theta equal 1/2? Pi over 3. 60 degrees, pi over 3. Okay? So that is this one. This is pi over 3. Okay? And so we have two intersections. What would this one down here be? negative pi over 3. Some of you might say that that is 5 pi over 3, which is correct. That is also 5 pi over 3, but we're not going, when we're filling in the area, we're not going around the long way. We're going clockwise from pi over 3, or from negative pi over 3 up to pi over 3. Okay? So it would get the incorrect answer if we integrated from pi over 3 to 5 pi over 3, because we'd be filling in a bunch of sectors over here, and that's not what we want at all. Okay? So we just want to integrate from negative pi over 3 to pi over 3. Negative pi over 3 to pi over 3. And then to get the green area, notice, looking at the original diagram, that green area is just a sector of a normal circle. So we don't have to use calculus to get that area. We could just say that that is, here I'll do it a different way up here. So this is a normal circular sector. And so its area is, what fraction of the circle is that? If it goes from negative pi over 3 to pi over 3, how many degrees would that be? 120 degrees, so that's 1/3 of the circle. So we do 1/3 of pi times the radius squared, and that is 3 pi. So we can get that area without using calculus because it's just a circle. Okay? If we wanted to use calculus to get it, we would just integrate from negative pi over 3 to pi over 3, and we would do 1/2 r squared d theta, where our radius is just constant 3. And that would give us the same result. So we can do that either way, use geometry or use an integral. Okay? So everyone go ahead and take out your calculators and figure out what is all of this together. Okay, I think if you type that in correctly, you'll get 4.653 as the area. Anybody getting that? Leslie? You can, yes, since they have the same limits of integration, in this case you can put them inside the same integral. Be careful about doing that in the future. You want to, that's why it's important to draw out the radii to make sure your limits of integration are the same, because we might have regions that are going to have different limits of integration, and as long as those endpoints are the same, you can put both expressions inside. But be careful, we'd have to write it this way. We'd have to do it as the integral from negative pi over 3 to pi over 3 of 1/2. We can pull the 1/2 out in front, and then we still need to do r squared minus r squared, like that. That would work. That would be fine. That is not the same as doing 1/2 the integral negative pi over 3 to pi over 3 of r minus r squared. That is not the same. Okay, so that would give you the wrong answer doing it that way. But you can put both expressions inside and pull the 1/2 out in front, and that'll give you the same answer. Okay? Other questions? Okay, so for the next one, if we graph r equals 4 cosine 3 theta, this is a 3-petaled rose that I have shown on the graphing calculator here. Does anyone remember the pattern of how you can tell how many petals it's going to have from the equation? If it's odd, then it's the number inside the cosine or the sine function. So in this case, 3 is odd, so it's going to have 3 petals. Okay, what if it's even? What if it was 2 theta? How many petals would it have? It'd have 4. So if it's an even number, you double it, and if it's an odd number, it's the same number. Okay, so for this one, since we have 3 petals, we have this, since we have 3 theta, that gives us 3 petals, and My general approach for all of these rose patterns, doesn't matter how many petals they have, is to just work with one small piece of the pattern and find its area and then multiply by whatever your multiplier should be. So in this case, I'm just going to find the area of a half petal and then multiply by 6 because it has 3 petals, so that would be 6 half petals. So if I can find the area of that half petal, all the petals are the same. And so it starts with theta equals 0, and then as always I'm going to trace out the radii so I can see what area is swept out as we integrate. Okay? Now it's easy to see that it starts at theta equals 0. It's not so easy to tell at what angle did I draw my last radius. Okay, so how do you know that it's pi over 6? Okay, so that's right. We want to know when the curve gets back to the pole, and so we set the radius equal to 0, so that means 4 cosine of 3 theta equals 0, and divide by 4, you get cosine of 3 theta equals 0. Now, what angle do I put inside a cosine, inside any cosine function to get 0? Pi over 2. Okay, we want pi over 2 to be inside the cosine function to make 0, so that means 3 theta would have to be pi over 2, and so, as Kevin said, theta equals pi over 6 gets us back to the pole. So this point, this ending point, corresponds to theta equals pi over 6. Okay, so now I can find the area of the half petal by doing the integral from 0 to pi over 6, 1/2 r squared d theta, which means the area of the whole rose is 6 times that. Okay, and you can go ahead and enter that in your calculator and see what you get. Oh, I left off the 1/2 when I rewrote that. One half r squared d theta. So I got 12.566. Any questions? Okay, next. We want to find the equations of the tangent lines every time this rose crosses the pole. So we said that it crosses at pi over 6, and then it crosses again there, and then it crosses again there. Okay, so what are the equations of those 3 tangent lines that we get when it crossed the pole? Okay, now you can choose to write your equations in polar or in rectangular coordinates using a y equals mx plus b, or you could use it, write the equations in polar form. Go ahead and work with a partner to figure out how you're going to come up with those 3 lines. Okay. Can somebody raise your hand and give me the equation of one of these tangent lines? Kevin? x equals 0 is correct. That is a vertical one. This one that I drew a little bit slanted is actually vertical. Okay, that is a vertical tangent line. So Kevin gave it to us in Cartesian as a Cartesian equation. What would that equation be if you wrote it in polar? Colin? Theta equals pi over 2. So theta equals pi over 2. Okay? So it's really easy to write the equation of a line in polar as long as it goes through the pole. Okay? Because the equation of the line is just the angle of that line as it goes through the pole. Okay? So we already decided that this one was that this curve reaches the pole. As we were tracing along here, we said this curve will come back to the pole the first time at pi over 6. So that is the same as the tangent line. So this tangent line is in polar, the equation would be theta equals pi over 6. Okay, so now we see that writing them in polar is a lot easier because if we just find the angle that it takes to get us back to the pole, that is the same as the equation of the tangent line there. And so what would this one be, the third one? Theta equals, you could say negative pi over 6 is one way to get there. Okay? And so those three all work. Now some of you may have attempted to do this in Cartesian, which first you'd have to do all this, which is to find the slope, you'd have to name y. Remember, y is r sine theta. So here's r times sine theta. Calculate the derivative. Do the same thing for x. X is r cosine theta. Calculate the derivative. And then you do dy over dx. And then you plug in the value, pi over 6. And we get a slope of 1 over root 3. Our y-intercept is 0 as it goes through the origin, so one of the lines would be y equals 1 over root 3x. That would be the first one. This would be the same as y equals 1 over root 3x. Okay? But my point is, it's not necessary to do all that. If you can write the equation in polar, it's a lot easier because we know that as this curve crossed the pole, the angle at which we were drawing the radii, or the radius, was pi over 6. So that is the tangent line, because when we're drawing the last radius, that's giving us the direction of our curve, and so that is the same as the tangent line. So you can do it that way much more easily than using the slope formula. But I gave you that option to do that if you didn't know how to do it in polar. Okay? And then the last thing is just another arc length formula to add to our list. Remember, we already had the Cartesian equation for arc length, which was integral from a to b square root of 1 plus dy dx squared dx. And then we had parametric, which was the integral from starting t-value to ending t-value dx dt squared plus dy dt squared dt. And now we have our third one, the arc length of a polar curve. And they all look very similar because they all come from the Pythagorean theorem. And that is the end of the book.